So we're going to be building a neural network from scratch using only NumPy and Python. Um, we're not going to be using any TensorFlow or any framework like that. Um, this video is going to be split into three parts. So the first part is going to be me explaining the neural network and the math behind it. And the second part is going to be coding it up in Python. And the third part, of course, is going to be the results. So I'm going to put on timestamps, and you can skip to whatever part you're interested in or watch the video in 2x speed. I do not really care or take offense to that. Other than that, let's just start. So we're going to be using the MNIST fashion dataset, which is basically a bunch of clothing pieces, pictures. Let me just double check. Yeah, it's 10 classes of pictures. So basically t-shirts, trousers, pullovers, dresses, coats, sandals, shirts, sneakers, bags, and ankle boots. So each picture is going to be one of those classes and is represented by a 28 by 28 picture. We cannot work with that. So we need to flatten every picture to a vector. So it's going to be, each vector is going to be a vector of 784 values. So each picture is a vector, and we do not want to process a picture at a time. We want to process the whole training batch. So we're gonna build a matrix from those from the training set. So each vector in this matrix is a picture, and we have 60,000, I think, pictures. So it's going to be a matrix of 784. Is it 84? I think 84. Yes, it's 784. It's not 48. Let me just fix that. Here, 784. All right, 784. All right. So the matrix dimensions are going to be 784 by 60,000. Now let's move to the architecture of the neural network that I am gonna build. So it's gonna be a very simple neural network. So it's gonna have only two layers. Let me make this picture a little bigger. So it's gonna have two layers. The first layer is gonna have 128 neurons, and the second layer, or the output layer, is gonna have 10 neurons. So the output layer has to have 10 neurons because there are 10 classes. Now the first one, I just chose the 128. It's just basically a random choice. So we're gonna process that matrix through these two layers, and we're gonna output hopefully a matrix that has the same shape of the training one, but each vector in the output matrix is gonna represent a value of a class. So let's take this vector for example. This vector, if we say the first position is the one related to the dress, so it's going to be 1 0 0 0 for the other 10 for the other 9 positions, and let's say that the second position is related to the sandals, so it's going to be 0 1 and 0 0 0 for the rest of the positions or classes. For the first layer, we're going to use ArrayLu activation function, and for the last layer, we're going to use a softmax activation function, so we can turn the values that we got from the first hidden layer into probabilities. And yes, that's basically it for the architecture. Now we move to the forward propagation, which is basically moving the input matrix through the network to get an output matrix. Now, we initialize weights and biases at a random at first. So the values of these weights and biases are going to be random, but the shapes we need to focus on the shapes. The shapes take 128 from the neurons that I chose on the first layer. The 784 the second dimension is basically needs to match the input matrix. Now for the bias is actually 128 by 1, but we need to broadcast it, which is basically repeat it to match the shape of the output, which is 128 by 60,000. So that's basically the intuition there. Now we get the Z1, which we process through the activation function, the regu one, which does not affect its shape. Now this is the A1 is the output from the first layer. Now we use the output from the first layer as an input for the second layer. Now again, we have other weights and biases that are going to be initialized at random at first. The shapes, of course, the second dimension here needs to match the input of A1, and the 10 from here comes from the number of neurons that I chose in the second layer, which was kind of forced because there are only 10 classes. And it's basically the same situation for the bias. The bias is actually 10 by 1, but we need to broadcast it, basically repeat that single vector 60,000 times to match the output of Z2. Now we take the Z2 and process it through a softmax function, and we get our final matrix, which is the output matrix. Now we're moving to the backward propagation equations, which is basically moving from the right to the left of the network in order to update our weights and biases. For these equations, it's not immediately obvious how we got them, but it's a situation. It's either you know how we got them or you don't, which basically is another topic that I cannot cover in this video. So you just gotta trust me that these are the back propagation equations for this specific network and these specific activation functions. So basically, this is the back propagation for the first layer or the second layer, and these are the backward propagation equations for the first layer. Now we're moving to updating our weights with gradient descent using the values that we got from the back propagation equations, which are dw1, db1, dw2, and db2. This learning rate is a hyperparameter that we choose that is not learned through the network, and here is just basically the new w1 is the old w1 minus that learning rate, which is generally 0.1 multiplied by dw1, and this is how we update our weights. Now through this motion of forward propagate and then backward propagate and then updating our weights, then doing it again and again and again and again, is how our network improves and basically becomes functional. So we're moving to coding the network up. All I've done for now is just import the dataset. If we take a look at it, we will see that the first column is basically the labels, or telling us which class the picture corresponds to, and all the other columns is basically the pixels. So I'm gonna turn this data into a NumPy array. So np.array is the function that does that. And I'm gonna split it into xtrain and ytrain. So xtrain is gonna be the data, all the rows. There's a separate testing data set that I'm gonna import later on. So all the rows from the second column to the last one, and ytrain is gonna be the first column. So ytrain. Why can I not type today? so all the rows and the first column. Let me just check. Yeah, that's what we need. Now, first thing first is going to be initializing parameters. So we go and initialize w1 is going to be mp.random. I'm going to use from uniform distribution. You can use you can initialize your parameters whichever way you like. So for the dimensions, it was 128 by 784. Now we just copy and paste this for the other three. So W2 was 10 by 10, I think. I realized I just made a mistake. W2 should be 10 by 128 right here. Where are we at? Yeah. Here. It should be 128. And here it should be 128. So, sorry for that. Yeah. B1 should be 128 by 1, and B2 should be 10 by 1. Maybe I should put all of these in a function, so let's just call it def initialize parameters. So it shouldn't really take any arguments. And it should return W1, W2, B1, and B2. Alright. Now we write the function to forward propagate. Let's call it fprop. It should take our training, X training dataset. It should take all the parameters. So we'll just put them up here. Alright. So for this, we just have to use these equations for propagating. So it's going to be z1 equals w1 dot x plus b1, and a1 is going to use ReLU of z1. Now we need a ReLU function, so we just code it up real quick. So define ReLU, and it takes x. Now we can just return mp dot maximum between x and 0. So if it's a negative number, it's going to return 0. If it's a positive number, it's going to return that number. Okay, now we go to z2, which equals w2 dotted with a1 plus b2 plus b2, and a2, which is the output, is going to use a softmax of z2. Now we need a softmax function also that we're going to write. Softmax, take x, and softmax should just calculate probabilities. So p dot exponential of x over np dot sum and np dot x. I think this should work. Let's just add axes equals 0 for good measure. Alright, so basically this is the forward propagation equation that should return to us. Let's just make it return everything for now. Maybe I'll use z1, z2, and a1 and a2. Alright, now we write the backward propagation equation. So define backward propagation, b prop. It should take x and y. I'll determine what it should take after I write the function. I'm gonna use these backward propagation equations. I'm gonna put them up here just to so it's gonna be dz2 equals a2 minus y. Now y needs to be one hot encoded, and I just realized that, and I do not know how to write a function of one hot encoding from scratch, and I kind of don't want to learn how to do that or figure out how to do that right now. So I just copied a one hot encode function from ChatGPT, and I made sure it works. So it does work. So we're gonna use it on y, because y needs to be one hot encoded. Yeah. So a little bit of cheating there. So w2 equals w2 equals 1 over the length of y. So w2 dot a1 dot transpose d2. So we need the derivative of the redo function, so I'm gonna implement that also. So I'm gonna name it define d-redo. So it's basically x, if x is less than 0, return 0, and if x is bigger than 0, return 1. Okay. So the arguments that it should take y. So it should take x, it should take y, and it should basically take z1, z2, a1, and a2, and also the w1 and w2. So I don't think it needs w1, but it only needs w2. Yeah. So w2. Yeah. Yeah. Okay. and it should return to us the uh, the derivatives of the weights, or it should return to us the dw1 to b1 and b2. So return dw1. Alright, now basically that's all we need for the neural network to function. Now we just need to write a function that puts everything together. So I'm gonna name it NN for a neural network, and we're gonna determine the arguments that it's gonna take after I write the function. So it's gonna be a while loop for it to propagate and forward propagate, backward propagate, and update. So it's gonna be a while loop. So while j is less than n, which is the number of iterations we're going to fix, do this forward propagate. So we take the forward propagation output and paste it here, and forward propagate everything, then backward propagate. So we take the outputs of the backward propagation, so backward propagate, and update the weights, which I need to write. So w2 equals w2 minus a learning rate times dw2. Let me just copy and paste this. So for w1, now we do it for b1 and b2. So it's going to be b1. So we change w to b. Here. All right. So we forward propagate, backward propagate, update the weights, and yeah, that should be it. So we return w1 nope, w1 w2 b1 and b2. It should take x, it should take y as arguments, and it should take basically all the weights so that we initialized here. Also it should take a learning rate, which I'm gonna put a default value of 0.14, and a number of iterations, n, which I'm gonna put a default value of 1,000 for it. Now return should be outside the while loop right here. Okay. Yeah, so I think we are done. One little note: we should normalize the values here so our network learns. So the values are between 0 to 256, I guess, for the pixels. So we need to normalize, so every neuron trains, because if we let the bigger numbers dominate, it's not really gonna train. The network's not really gonna learn anything. I wanna put here the accuracy while it's training. So after 20 iterations, I wanna paste the I wanna show the accuracy. So j equals 0. So this is a little code to print the accuracy after 20 iterations of the network. So prediction is gonna equal mp.arg max. So here is basically telling it to return the position of the biggest probability in each vector in the output matrix. So, and print, let's just accuracy, 2 points, 2 points, okay. And basically it's gonna be np.mean. So when our prediction equals the true values of y, and let's just put it times 100 to get the accuracy. Yeah, so basically that's all we need. And so it didn't run. I forgot to put the multiplication symbols here. So hopefully it runs now. Okay, it runs. So we just put our parameters here. Well, we need to initialize them first. So initialize parameters here. Okay. Now we put our parameters here and the neural network. Okay, and let me just normalize it here. Okay. All right, now hopefully this works. Oh yeah, it's x is not defined. I should use x train and y train. My bad. So y underscore train. Now hopefully this works. No, it doesn't. Oh yeah, basically I did not transpose the matrix examples. So my examples are row wise and they need to be column wise. So here I should put in here I should transpose it. So once again, I'm debugging live. So another bug. And also this one should be transposed. The one hot encoded vector should be transposed also. Here it should be 2 points. My bad. I'm just doing way too much. Oh, what's the problem? In backward propagation, y is not defined. Yeah, so y here it should be lowercase y and not uppercase. All right. So after I fixed multiple issues that I had with the code, mostly typos and such, basically here it was NO instead of NP, here it was 1 equal sign instead of 2. Here I never returned the p-value from the, or the probabilities from the softmax. So after I fixed all that, I'm going to leave the code, by the way, in the description through GitHub, or I'll see. It's currently training on 1,000 iterations. So after 40 iterations, we have 21% accuracy. So we're just gonna wait and let it train. So after 1,000 iterations, it finished training and it got accuracy of 73.9, basically 74. So it's basically good enough for me. While it was training, I wrote 2 other functions. The first function is a function that takes an input x, a matrix x, and the y label, the true y label, and just calculates predictions and the accuracy. As for the second function here, it just basically plots the picture and tells us our predictions and the actual value of the example. I imported here the test set, and I'm applying the first function here on the test set. So it got an accuracy of 73.9 on the test set. As for the second function, so we give her we give it the predictions and we give it the true value of y on the test set, and we choose an example. So say 85. So the prediction is a bag and the actual is a bag, and here's the picture. Let's take another one. So like 1,500. So prediction is a t-shirt, the actual is a t-shirt, and yeah, let's see if we get one wrong. I want to see. Yeah, so prediction is a coat and the actual is a dress. Let's see another one, 23. So prediction is a trouser, actual is a trouser. You get the gist of it. That's basically it.